Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, let's do the Python part of the Facebook profit model. If you have not watched the theory lecture, I highly encourage you to go back and watch there and then come back to this video. So as always, you can find all the codes on my GitHub accounts, go to the deep forecasting course, and then find the Facebook profit module. The name of the module is Profit and NeuralProphet. So there are two files I want to cover, Profit Basics and Profit Advanced. Just like the other module, the past couple of modules that we did, I have an intuition kind of notebook for you to be covered in the basic version, and then we do a more advanced version here. So I love the documentation of this package. All right, so let's go ahead and open it in a little Colab, and then hopefully it's gonna run. And we don't need CPU. It's a simple. Wait, sorry, we don't need GPU. It should be a simple CPU. I'll see how fast it goes, and we're not parallelizing anything. So probably we can run it with a simple CPU. Station runtime CPU. Okay. All right. So forecasting at scale. We know what we mean by scale, right? Okay. These are kind of, the paper. Please give it a try. The paper is really straightforward. It's not that it's that technical. You can do it. And if not, just read the slides and definitely check out the documentation. This is one of the best documentations I've ever seen on a package, which is really cool. Cool example. And I'm going to cover almost all of it today. Almost all of it. We'll see. We don't get into the outlier we don't get into this one or handling shocks or additional steps, but yeah. All right. We're going to have it open. And yeah, walk through the code. So let's see if it works. There you go. So it's already built in. Okay, so we don't need to install it. On your computer, just do pip install. You can do either pip or conda, both of them works. All right, so let's import the packages, importing dataset. So first things first, PyCaret is expecting two columns, and these are the names. The name is DS, it stands for your dates, and then and Y is your target journal. You have to rename the dataset, whatever you're doing. So for example, for this intuitive notebook, I'm gonna work with airline passenger, and then for the next one, we're gonna look into a business task, business time series. Airline passenger is not necessarily a business time series, right? Well, by business time series, I mean, we talked about the properties last time. It has multiple seasonalities, and yeah, like something to do with holidays a ton, actually. Holidays matters a lot for business data. Okay, so let's read the dataset. We have seen this before. Right now, the dataset the date comes as indexed, right? So we have to change it. Again, remember, two columns, DS and Y, and your DS should be in this format, either year, month, day, or year, month, day, and hours, minutes, and seconds. Okay, so both of them works. So the first thing I should do is just prepare the data for profit. So I'm going to reset the index. So if I reset the index and set and in place is equal to true, it's going to replace this one with index from 0 to whatever, and then create a new column, call it month, and then that's going to be the dates, right? So this is what this line is doing. I'm going to rename the columns to DS and Y, and then this is not required, but it helps us if you want to do visualization for yourself, right? Profit doesn't need, as long as your date format is correct, it can handle it. But I'm going to change it. So this is my personal preference. I'm going to change it to date time, because down the road, you're going to play around some visualizations, etc. So this is a good habit. All right. So this is the new data set. Okay. DSY, and this is your index, which is basically some numbers. We can plot it, right? So this is our plot. And as you can see, it's upward sloping. There's a trend, there's seasonality, and the seasonality is multiplicative, right? We can do all these things just like BTS with profit. So we have a multiplicative seasonality. Just keep that in mind. Yeah, so far so good. But this is relatively a smaller data set, right? So especially if you want to capture multiple seasonalities or yearly, weekly, place like that, you need more data, right? And in this case, we only have 144. I'm going to use the first 120 for train and then the last couple 24 months for test. All right, model fit. So here's the basic version. Let me actually open. This is our, I'm going to go on. So we're gonna be feeding forecasting and then play around with the parameters, change point, seasonality, and holiday. Do you remember that 3 things that I wrote on the board last time? You know, there are 3 knobs you can play around with. So we're gonna open up that thing in Python today, and then we'll talk about evaluation, cross-validation, and diagnostics. Okay, so that's the plan. So just like PyCaret, this is pretty straightforward, right? This is my instructor, right? Yeah. I create an object, profit, open close brand, nothing there. So it's going to use the default values, right? So actually look at that. This is the compiler and then collab, right? So if you just hover that profit, open close parentheses, it shows you what is inside. So you can play around with growth. By default, it's linear, change points. Maybe take a note. Okay, so when it says change points none or number of change to 25, by default, let me actually explain these 3 first. Change point none, number of change to 25, and change point rate 80. Okay. So by default, it's gonna look at the first 80% of your data, only 80% of the first 80% of the data, and use 25 equally spaced splits. If you have, so for example, if I go back here, it's going to look at the 80%, whatever you're passing. If I'm passing the entire thing, it's going to look at the 80% and literally equally space them 25. So it's going to use that one. These are the candidates for change points. You're not going to use them necessarily all of them, right? But it's flexible enough. It says that if in the 80% of the data, you're giving a model 25 times chance to change the direction, it's flexible enough. You rarely need 25, right? And how we can tune that? By changing that delta parameter. So delta parameter that we talked about last time. So it's called change scale. So let me show you. Okay. And yearly seasonality, by default, it's auto. Weekly seasonality is auto. If your data set is, if you're working, for example, with monthly data, the weekly seasonality should be turned off. But then this auto is going to take care of that one, right? So daily seasonality again, auto holidays, non-seasonality mode. So this is your added to multiplicative thing you can have. So these are the most important things, those 3 numbers. Seasonality prior scale, which is by default 10. This is the magnitude of the seasonality. 10 is already a large number. Okay? And then we have holiday prior season and scale. So again, by default, it's 10. And we have change point prior scale. By default, it's only 0.05. Well, it only is relative, right? We're going to play around with all these 3 knobs. So in my opinion, these are the most important knobs that you can play around with. And then you're doing hyperparameter tuning in NeuralProphet, we're going to change these 3 values. Okay, so this is, by the way, the hyperparameter tuning thing that comes with NeuralProphet is super handy. So we're going to look at that too. This is just like Greek search that we did in machine learning, right? So we did Greek search to find, we created a dictionary for hyperparameters that you want to tune, and then we did a Greek search to find the best parameters. All right, so if I run this line, so basically the model has been fit now, and that's it. So I fit the model on the entire data frame, everything. And yeah, so no pre-processing. I could have gone and used box-cox transformation because, again, you're an expert, right? You know that this is stringing at you that, hey, there's this growth that we need to take care of. You know, the variance is growing. So how can I control the variance growing? I can do box-cox transformation or log transformation, right? But again, you're not going to touch anything. You want to see out of the batch how the NeuralProphet work, and then later on we're gonna correct it. Okay, so again, just a couple of lines. Profit, create an object, fit it, make some prediction. That's it, right? But before making predictions, we have to create this data frame called future, and this is a terminology that I think everybody is using when it comes to NeuralProphet, because in their documentation, this is the way that they are doing. If you do a quick start thing, Where's the click start? There we go. Yeah. So this is a terminology that everyone is using. So I'm gonna stick to that one. I don't want to make it complicated. Okay. So future is the name of the data frame that you need for forecast, right? What is it? Once we're doing univariate time series forecasting, if you want to predict into the future, you just need a column of dates. So for example, if that date go from day 1 to day 24, in this example, month 1 to month 24, the model knows that you want to make prediction for the next 24. This is how you specify it, right? By default, the frequency of this future data frame is daily. So if you had a monthly data set, you have to change it, right? And these are, so we're going to say MS for monthly data. This is month starting the start of the month, right? MS. And I'm going to say, let's make forecast for 24 periods, right? From this 24 onward, right? And now if I look at the tail of it, as you can see, it goes to 1962. Remember, our data finished in December 1960. So 2 years from there is December 62. So that's your feature data frame. Okay. Now I have the feature. I want to make some predictions on that feature, right? So again, just it's a good practice. Always keep track of the shape and size of the data frames that you're working with, right? My original data frame was 144, 12 years. And then this one, future, is 168. So it means that this is a data frame that has time index from day 1 to the last day that they want to make forecasts. So it's going to make predictions both in sample and into the future. Does this make sense? Okay, great. In sample predictions and future forecasting. Now your model has been trained. You saved as M1. I'm going to make predictions off of that, and you have to pass predicts of what on these dates. Remember, in this feature, there's only dates. And yeah, actually, in your forecast, there's a lot more. Let me create a new cell. This forecast has a lot more. Okay, so these are the columns that it comes with that forecast. So these are the columns that you're typically interested, right? The date itself. This is your prediction, lower bound, upper bound. So this is your interval. Okay, but what else comes with that? So your trend components. And again, this is lower upper bound. There's a lower and upper bound for your trend component, so you can get a confidence for your trend component as well. And there's this thing called additive terms and additive term lower band and upper band. So what is additive term? Additive term is basically a combination of your seasonality and holiday effect, right? So what else do we have here? Let's go back all the way. So this is your yearly seasonality. If there's the weekly, start figure it out. There's no weekly here because your data is monthly. It doesn't make any sense, right? And multiplicative term. So by default, that seasonality was additive. So that's why we don't have multiplicative. And this is your prediction. Okay. So basically, if I go ahead and take this one, this yearly, minus 21.37, and add any kind of other impact we have here, we don't have anything. But it's going to add it up to this, right? You see that? Additive term. Well, let's go back. Additive term, this one. This is a combination of any impact that the weekly seasonality, yearly seasonality, it's going to combine them together. Okay. So why do we need them? Because we want to visualize them. So let's actually, so in our forecast thing, this is the data. And remember, the forecast, I think they couldn't call it anything else. But remember, this is the predictions for your train and into the future. We call all of them forecasts. For the historic data, it doesn't make any sense to call it forecast, but it is what it is. Okay, it's not bad. All right. Then when it comes to plotting, we can do just M1. This is pretty much like pie-carrot, right? You had a trained model off of that, plot something, cross-validate something, and then compare models, right? Plot forecast. So this is going to give you forecast both for in sample and out of sample. So your model is doing well. Your eyes has not been trained yet. You haven't seen many NeuralProphet charts yet. But what do you think? Is the model doing a good job, or The black dots are your actual observations. That's why it only goes to 1960. The blue chair is your forecast. The white, the shaded area is the confidence interval. What do you think? At least at the beginning, it's okay. But look at that. These peaks are over predictive. At the end, those peaks are kind of under predictive. You see that? So it's missing that multiplicated aspect of seasonality, right? Because by default, it's using additive seasonality. We could change these things, right? So, and of course, it's not going to figure those things on its own. So you have to have some domain knowledge, right? So you're going to look at this time series and say, okay, it's obviously missing that part, and yeah, let's do something about it. So that's the next step, right? So we're gonna fix all those stuff. Okay. All right. Then a cool thing about this package, you can call the components, right? So I say plug components, and these are the components. The reason that I'm saving it in a fig, because if I just erase this one, it's going to create two of them. So either I'd have to do this to get rid of two plots. This is a notebook thing, or I have to save it as a fig, right? As a figure. So now there's a trend component, and there's yearly seasonality. Okay, so we have seen something like this with ETS as well, which was doing a perfect job. And so this is a good example for you guys that probably for super well behaved data set like this, with periodic seasonalities, regular seasonalities, there might be better models out there, right? And then ETS is good, Areno is perfect, and then I think any kind of model with autoregressive nature in it can capture this, right? But here we're lacking these things. We're gonna fix them. All right. So are we good with the I'm done with the model fitting and making forecasts and then plotting the components. You're gonna look at these components. Depending on what you have in the data, it generates more charts for you. For example, we can have trades, yearly, weekly, and then later have some additive components, some auto regressors if you're doing or not. So we're gonna look into that. Okay. So just be aware, this is not always 2 charts. So sometimes it goes to 5 charts depending on what you're doing. So holiday effects is going to be plotted, and we're going to look into that. All right, so here is what I expect you to remember from our theory class. So we're going to play with 3 things: change points, seasonality, and holidays. So maybe I can open this part quickly. Okay, so these are the components, right? So we're going to start with the trend components. Remember what was inside the trend component? There were a couple of ways we could model the trend: either nonlinear saturating growth or linear with change points. Which one do we need here? The linear trend with change points, right? Because your airline passenger, it doesn't have this notion of saturation. If it you can argue that there's a limited number of people living on Earth, but your product is not that widespread. Okay, it's not Facebook account that you say, okay, it goes to billion. This is airline passengers, so there's no way it goes more than a certain number. So that's why I'm not worried about this kind of modeling it as a growth. So it's not going to be a growth; it's going to be a linear trend. So I'm going to introduce some change points. So let's do. And we talked about the change points, that there are a couple of things you can do, right? You can how many change points you want to put there. By default, remember, it's 25, and then how do you want to tune it, right? If you want to see 25 change points, or you want to see 2 or 3. How can I do that? By changing this, the prior distribution for this delta, right? And yeah, let's look into that one. Okay. So probably will automatically detect. By the way, I borrowed this part from the documentation. So whatever you see here in the notebook, it's a combination of me, documentation, and ChatGPT. Okay, so this is, but it's good. It's some of them are, you cannot find them in the documentation. It's part of the paper. So the change points allow the trend to adopt the proper, obviously, how many of them we're going to use. So, and our key variable to play with, key parameter, is delta. It's coming from a Laplace distribution. And if you don't know what is Laplace distribution, Laplace. I think all of you guys know what is normal distribution. Plus is just a little peak. No, it has a fatter tail. So it has two components. Just like on a standard deviation, you call them standard deviation here. It's just there are two things here. It's a location parameter, and then you have a scale parameter. Location is where you are. So we are using Laplace 0 and something. Remember, 0 on top. So 0 means that we're at the center, and then tau is the larger the tau. So this is your tau, right? The bigger the tau, the more picky it becomes, and then you're gonna have look at the problem. This is a density function, right? This means that you're gonna have more of those number of. If I increase that tau, it's gonna increase the number of change points to the model. If I set it to 0, you're gonna be some one line. All right, so again, here's an explanation. So setting tau is equal to 0.1 rather than a more conservative value like 0.05 allows the model to detect and adapt to changes more aggressively. But I think a picture is better, 1,000 times better than a word. So let's play around with those things, right? Again, by default, there's 25 of them in the first 80% of the data. So how can I make those changes? I'm going to make a new model, call it M2. So let's keep track of these things. M1 was the base model, defaults, no anything. M2 is the one that we're trying to play with, right? So let's start with playing the number of change points. So this is change point prior scale. Again, this is a default value, 0.05. And change point range, 80%. I can change it to 90%, and it's going to cover the first 90% of the data. The reason that we go to 80% is that we don't want to overfit, especially when you get close to making forecasts. Yeah, if I say, okay, use 100% of the data and then create change points, obviously the very last one is going to be kind of cheating, right? We don't want to overfit. Yeah, so this default works in many situations, but not all. So sometimes you have to play around with that. So I would say don't go beyond 90%. So I typically do 90%. Because especially if there's a clear structural shift in the time series that if I have the luxury to have access to that part of the data, I would incorporate it. Let me tell you what I mean by that. Imagine you're using quarterly data and get from 1950s to 2023, right? This is quarterly data. Look at the history of interest rate in the US. 2 years ago, it was 0. But within the 2 year, now they're minus 5%. So if I have that information, I want to incorporate it. You know what I mean? So that's why I don't. So if the data is between 1950 to 2024, I want my models to see what happened to the interest rate 2022 to 2024. So again, it depends on the context. Don't think that it's always 80% or always 90%. Depending on the context, you're an expert. You have to figure this out. Okay, so do we need to add that part of the data as well? So in that example that I gave you, the answer is absolutely yes, because that was a regime shift, regime change, right? All right. And then now this is your model. You're going to fit it. I did fit predict in one line because again, we know how it works out. And then this is a figure. This is the figure itself. I'm adding the change points by this add change points to plots. Okay. So if I do add change point to plots, and then this is just says that take this figure and then add the change points to that. And then your model is N2 and you want to plot the forecast, right? So if I run this, it is. Yeah, I'm plotting the forecast and components. Let me actually do it separately because. Okay, well, so here again with the default value. So it seems that if I go back, it was using, so maybe it's not obvious here. I didn't change anything. I'm just using the default values. This is a default value of Facebook profit. It was using 4 change points, right? So maybe there's one here. I can see with the naked eye, one here, and etc. Right? But if you plot it here, so it's like a regularization parameter. Remember, you see that they are equal in space because the model is using the first 80% and putting 25 lots. And now I'm adding this regularization parameter. The larger that thing, the bigger penalty it gets. The smaller number of splits it's going to pick. Does that make sense? It doesn't need to be close to, this is just an accident that they're close to each other, right? So it might be one of them here, one of them here, one of them here. So let's play around with that. So if I, for example, instead of 0.05, if I do 0.5, you see, now it's more relaxed. It lets the model to just adjust more frequently. Now, instead of 4 splits, I have how many cutoffs? 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. 11 cutoffs, right? So do we need that many? Again, it's your call, right? So the whole point of this Facebook Prophet as agent in the loop thing is this. I can see it. I have, as an expert, I know something about it. I like to make some changes, right? So maybe it's overkill. If I do, for example, 10, what do you think is going to happen? It's going to do 25 lines, right? Well, maybe we need one more here. But if you count them, it should be 25. Okay. And so maybe, and if I do something very close to 0, what do you think is happening now? If that top is close to 0, what happens? It will say, well, basically, look at the linear line with those splits. It's going to be something like this. It's going to impose more restriction on how many number of splits you're going to use, right? So basically, if you change that knob from 0.001 to some more large value, then you get from no splits to 25 cutoffs at most. And again, 25 is not a magic number. This is what the authors of the paper decided to pick. And then honestly, you never use more than 25 is too much. So you never get to that point at all. Because if you want to make forecasts with 45 different splits, probably it's gonna overfit anyways. You remember, this is your train. What will happen in the future? You have no idea, right? Yeah. And just imagine replace this 12 dataset with stock and then talk about 35 different splits or products. It's gonna be ridiculous, right? All right, so this is so far. So and let's actually bring it back to 0.5. And then now I can play around with this 0.8 thing. I can make it 90% or 95%. Just look at that. Well, you need more cutoffs to see that actually. So maybe. It's using almost to the end of the data, right? Because I said 95% of data. If I say 50%, it makes more sense now. Going to use the first 50% of the data. All right. So any questions so far? Good. So you have a variable called ta, and that ta decides how many products you have, or you should have. And there's machine learning language. How do we do that? So we're going to do cross-validation, look at the performance, and then see, for example, look at the average mate for different cross-validated data. And this is a tuning parameter. We can come up with some preset values. For example, we say 0.001, 0.01, 0.05, 0.1, and et cetera, right? Depending on your compute power, you can go crazy. You can try 100 combinations. And the cool thing is that this package, it's parallelizable. So that's really cool. So you can parallel processing, and it's super simple. I haven't done it in Colab, but I will show you the documentation if you want. You have to just install another package. If you run it locally, it's going to run on different cores of your CPU. So this is super simple. Okay, so that was the first part. The second one is seasonality. So let's go back to the slides. So for seasonality, again, you're using this Fourier series, and there are a couple of things we need to pay attention. This is n, how many of these terms you want to add, right? You know, how many of these cosine and sines you want to add. You're going to have 2n of those ones. So if n is 10, you're going to have 20. And there's some default values. For example, yearly data, n is equal to 10. For monthly seasonality, by default, it's going to do 3. So again, but the whole point is that how many of these sine and cosine you want to add as a regressor, remember, as a regressor to the model. This is your features, regressor to the model, and then how you can play around with its magnitude, beta. So beta was something that told me what should be the magnitude of these sine or cosine, right? Because this is your feature, x1, x2, x3, and etc. How big or small do you want to make that impact? It comes from a distribution. Beta is normally distributed with average 0 and standard deviation sigma. If sigma is large, this beta you get large. You good? So this means that in this parameter, if I increase the sigma, which is the variance of beta, that beta can be larger. That beta is larger means your cyclicality is going to be the more exaggerated, right? So I'm going to show you an example in Python. It makes perfect sense. So this is what I just told you is here, right? So feel free to read it for yourself, but basically the larger that sigma, if the sigma is larger, your beta can get larger. Does this make sense when I say if sigma is larger, beta can get larger? Because that's the variance of beta. So if sigma is larger, you can observe larger betas. And those larger betas are going to emphasize more on the seasonality with higher magnitudes. There are many other ways you can customize seasonality. So let me show you this one, which I think is most effective one. But you can have, we're going to click on this documentation. We're going to check it out together. But let's do this part together. So first of all, the first thing I need to fix, let me do it additive before you. So this was what the model was lacking, right? It's underfitting here and it's overfitting here or overpredicting here. Not, sorry, overpredict, underpredict, not predict. And so the first thing I can do is change the seasonality mode. If I change it from additive to multiplicative, probably it's going to solve this far. You see that? You see the difference? Okay. This should be obvious, right? You have the theory background. Now, this is the seasonality prior scale. This is your sigma. So this is your sigma. If I increase that sigma, beta can get larger. Default values are additive and 10. So right now, because I'm saying that 10 is a large number, according to the documentation, 10 is a large number. It means that you can tell the seasonalities to go crazy, right? But we can capture any kind of seasonality with high magnitudes. If I change it to a very small number, what do you think I get? Let's do 0.001. Before me running it, what do you think I get? If that thing is a small, it means that your beta is a small. If beta is a small, what happens to these things? They're going to completely do that. Let's say extreme case, beta is 0, we're not going to see any seasonality, right? So, sorry, if I do a small number, this thing will, the seasonality should be wiped out. Let's see if that's the case. But before that, look at the model components, trend, annual seasonality. Okay, so let's look at that one. There you go. Okay, you see that? So, and what I want you to pay attention first is something like this, guy. If your model is not capturing the seasonality enough, do you see what happens to the confidence interval? This confidence interval is talking to you. It says that I'm not confident with my predictions. Okay. So that's why you see an upper bound and lower bound that's crazy. So if I go back and then tune this parameter to something, I don't know, it can be 0.5, by the way. Oh, this is 0.5. Yeah. Do you remember I told you 10 is overkill? 0.5 was enough to capture this seasonality perfectly. And look at the confidence intervals. They're narrower. So it means that your model is confident here in the predictions. Okay. All right. So sometimes you will see, look at that. Do you see this a little bit of like shaded area in here? This is, for example, it says the model is not, so the model is super, these are the lower bounds and upper bounds of your trend. You remember the trend component had lower and upper bound? So we're visualizing it. It's doing a decent job here. And here it's having a little harder time at the end of the trend. You see that just a little bit. So that's the uncertainty in trend. And you can see uncertainty in seasonality and etc. Okay. And overall, this is overall uncertainty of the model. All right, so that was the second thing. The third thing we're going to look into is holidays, but as I promised, let me show you the seasonality thing. The documentation for seasonality. So this is where I think the Prophet package shines. This is a seasonality part. Seasonality and holiday effect. So the things that you can do with it's super fascinating. So I think let me do both of them together because the documentation starts with holiday. Look at the holiday. So we're going to look into the Python code. You can have a list of your own custom holidays, right? For example, we can have playoffs. And it's a data frame with 2 columns. The first one is holiday, the name of the holiday. The second one, it's the dictionary. And the second one is at least keys and items, right? Second one is the bit DS. So what is the date of those holidays? These are the dates of playoffs. And as you can see, I can have multiple calendars. So I have a calendar for playoffs. I have a calendar for Super Bowls. I have a calendar for US holidays, different countries' holiday. And but the thing is that you have to make sure this dictionary that you're providing for holidays, it goes from day 1 in training to day T at the last day of forecast period. The last day of forecast, right? So for example, if you're forecasting 36 months into the future, you have to include 3 years of holidays. And this is literally manually. You have to do it manually unless you're using some public holidays like US calendar. So there's this holiday package in Python that gives you access to the different countries' holidays. You don't need to write them manually. So that's one way you can specify. And then last time in class, you remember I told you that maybe you want to see what is the surrounding effect of that day. Black Friday, I want to see the day before, the day after. The day after that is Black Monday or Cyber Monday, right? So you can play around with that. Lower window, in this case, I say just look at the holiday and the day after. Okay? Does this make sense? We can change that. For Super Bowl, again, not yesterday, but the day after, because that's, well, I would say Super Bowl, I would definitely do -1 here instead of 0. Because I want to go 1 day before too. Anyways, what else we can do in terms of holiday and let's say seasonality, right? So the thing is that in the forecasting part, you can just look at the predictions on those specific days, right? So this is super cool, right? So for example, we want to see Super Bowl effect, and then so here's 2 calendar. I could only look at the Super Bowl and then just look at the numbers for Super Bowl. But here, because there's 2 calendar, you can, of course, there's not 100% all of that, right? But you get the idea. So if you're dealing with a problem and then you want to specifically see what happens during Super Bowl, the day before and after in this time series, NeuralProphet is going to make your life a lot easier. A lot easier. Okay. You can do it for any other model, but this is all automated, just one line. What else you can do? Once you do that, once you add the holidays, you're going to see an extra components plot. So this is going to help you a ton, right? What happens during those holidays, right? So here's a positive impact, positive, positive, positive. It can be both positive and negative. So this is the impact of holiday on your target variable. This is your trend. Impact of holiday on target variable, week with seasonality, year with seasonality. What else we can do? Built-in country holidays. So this is what I'm going to cover in the next notebook. Again, you can easily use, for example, US calendar. Right? We have to train an object and then add country-specific holiday. It can be US. In our example, we're going to do Germany, which is DE. And if you're wondering where the list of you can get the list of country names, just check out the holiday package, Python package, just holiday package. Holiday. You will see a list of countries here somewhere. Yeah, there you go. List of countries. Okay. All right. So that's another thing. Again, you can see the name of those holidays. We're going to see the German holidays in the next notebook. And what else we can do? Let's see. Subdivision part. So this is also, for example, again, this is for specific countries. Okay, so now we're done with holidays. This is the seasonality part that I just covered, right? For seasonality, there is this parameter we can play around with, seasonality scale, prior scale. And yeah, so let's see, specifying custom season. You can do custom seasonalities too. So this is so cool. So for example, for your entire data, you can say there's no weekly seasonality. And then you're going to add monthly seasonality with different order for a year as well, right? So if I make it larger, it's going to emphasize more of those things. But instead of doing it this way, I prefer to turn that knob thing, that delta thing, this one. I prefer to play around with this beta. Okay, so what else? Yeah, again, this is very flexible. Seasonalities that depend on a lot of factors. Just read the document again. These are some examples for you. Obviously, we cannot cover them all, but there are so many things you can do. This is the one that's my favorite one. So this is prior scale per holiday and seasonality. And the cool thing is that you can have multiple different kind of seasonalities or even custom seasonalities, and you can tweak and twist each of them separately. This is cool. So when you change that prior scale, it doesn't need to apply to all seasonalities. Okay, prior scale will apply to one of them, for example. Yeah. So this is for all of them, and then you can change for one kind of seasonality or for one of the seasonalities if you do them separately, right? It's like in deep learning where we were stacking layers on top of each other. It reminds me to that kind of notation, right? So we have this M, and we're gonna stack a bunch of things to that. So we can stack extra regressors, extra calendars, extra seasonality, etc. Okay, so that's cool. Yeah. There you go. So let's go back. So we talked about seasonality, holidays. I barely covered it, right? So again, for holidays, we have yet another parameter, which was gamma. So remember, this Z is a bunch of 0 1s. So basically, if that date that you're making a forecast is a holiday or not, if it is, how much you are emphasizing, like this is your kappa, and then kappa is the magnitude of your holiday effect. That kappa has a distribution coming from normal with standard deviation gamma. So when you're playing around with this thing, so this is your gamma. This prior scale, this is your gamma that you're playing with, right? If you make it larger, it's just going to make the impact of holiday larger. Okay. So here, just to showcase, I'm going to basically make it a random holiday. I call it my special holiday, right? So this is a dictionary. This is a data frame, right? Coming out of this dictionary. It's called my custom holiday. And I named that holiday my special holiday. And there's only 2 dates in that. Yeah, just for fun. And I care about the day after that, not the day before. So that's how I set it up. So now I have my custom holiday thing. I want to add it to my data, right? So look at that. This is my M4 profit holidays. I'm going to add my own custom holidays and holiday prior scale. Let's for now use 10. Then on top of this, look at that. This is where I told you to like deep learning. You're adding layers on top of layer. On top of that, I'm adding country holidays. So if I say country name US, it's going to use US holidays. So I think I'm done here, and I'm going to go ahead and make a forecast. Forecast fit predict. Okay, and let's look into that. So it's not going to make a huge impact on this data set, to be honest, because again, we can look at the holiday effect. But remember, this thing is using monthly data. So probably if I see anything, let me show you the holiday. So this is a holiday impact. And it seems to me that at the end of each year, or maybe even in the summer, sometimes it shows, sometimes it doesn't. But don't read too much into holidays if your data set is not daily data. Does it make sense? Because the only holiday that I can see here, actually, let me actually show it to you, which is exactly on the first day of the month, is New Year's. That's it. Do you have any other ones here? Probably not. By the way, off of that object that we created, if I say train holiday names, this is the name of all the holidays that the data is observing, right? Remember that I created this one? We can have a bunch of different version of holidays in one object, right? So yeah, so that's probably why we only see that day one effect. Day one is the first day of the year, and according to the model, the number of passengers is negatively impacted for that. Okay, does that make sense? Maybe exactly on the New Year day, there's less passengers. And of course, the magnitudes can talk to you, right? So look at the magnitude of the data. You're here, we're scale up 300, 400, 500. And this is, we're talking about 5 to 10 people, 20 people. So it's not bad. So you can look at the scale of the holiday effect as well. All right. So are we good so far? Okay. So model evaluation and diagnostics. So the cool thing about Prophet package is that it can do cross-validation, and this is so fun. And that's the part that in the paper it's not clear what they do, but in here the documentation is perfect. By the way, documentation is really good, but the paper doesn't discuss the cross-validation. So let's do. Where are we? Okay. So here, how's going to do it, right? It's going to say, use this part, we'll call it train part. And then there's this thing called horizon and a cutoff, right? So there's another thing called period. So let me actually familiarize you with 4 terms: initial, cutoff, horizon, and period. Okay. So let's start with these 3, and then I'm going to add the period. So initial means that use this data to train. Cutoff means that's the first day that you're going to start making predictions, forecasts. Horizon is how many days you want to forecast. Okay, are we good with these 3? 100%? So let me add another one, period. So period is how often do you want to, how do you want to roll over this window? Remember, guys, this is time series cross-validation. This is one metric. If I make a forecast here, I can calculate the mean absolute percentage error for this wired data. That's one number. But I'm going to say, let's roll over this thing or the entire data set and make 10 of those. This is the whole idea of cross-validation. What time series cross-validation, right? I'm rolling it over. So I'm going to say, for example, if horizon is 1 year here, I'm going to use a period of 6 months. So what does it mean? It means that roll the entire thing 6 months, make a prediction. 6 month prediction, 6 month. Does that make sense? And you can repeat it as many times as the data allows. We're going to see how many times, for example, for our data set it is. But instead of working with one metric, one mate, I have 100 mates now over the entire data set. This is the whole idea of cross-validation. And I take the average. That average mate is a fair estimate of the performance of the model in a test set. And this is all automatically done in Prophet, so let's do it. Okay, but obviously you have to work with the model. So I'm going to create the model number 5, which is a combination of everything you did so far, right? So this is the layer component of it, right? So I can say, I like the idea of having this change point priors, prior scale, having the change points. I like the idea of seasonality be multiplicative. So I'm twisting this seasonality prior scale. Right now, I'm not touching the default value. It's just 10. I didn't like the idea of holidays in this data set because my data set is monthly. So I don't add that layer. I don't add that extra layer. And this is it. This is my model. If it predicts, forecast, and you can plot the change points as well as components, right? So this is the model. I want to run cross-validation with this model. Okay, so let's do time series cross-validation. So for time series cross-validation, you have to import cross-validation, and we are going to need performance metrics. And for visualization, we're going to need plots cross-validation metrics. Okay, so remember those 4 terms: initial, period, horizon, and then cutoff. So initial, I'm going to use 5 years of data. So this is the trickiest part when it comes to working with Prophet, because if you don't get this part, it's the process doesn't make sense, and then you'll be kind of confused. Whatever Prophet is producing is daily, or it's so if your data is monthly, and if you want to have 4 years of data, so I have to say 5 multiplied 365. Okay. And then I'm going to roll this thing over every year. So that's my period. My forecasting horizon is 2 years. 2 years into the future. So 2 years into the future means how many observations for your data set? 24. Are you good? So if you want to do 24, so you have to you cannot write 24 here. This is a common mistake. 24 doesn't make any sense, right? So you have to do 2 multiplied 365 days. Okay, so this is my initial period and horizon. So again, 12, 24, and this is 60 in my data set. You following? Because that's a monthly data set. All right. Now I am going to create the data frame, call it df_cd. And again, these are very commonly used terms. So I'm copying everything from Prophet documentation. You have to pass the model. M5 is what we decided to work with. Initial, period, horizon. Okay. I didn't specify cutoff. The cutoff is going to be exactly when the period ends. Well, when the initial ends, the cutoff is right there. Okay. So this is going to take a little time, depending on. Okay. Yeah, if you run it locally, things are kind of different. Well, anyways. Now, what is inside that data frame? So there are a bunch of stuff that I want you to pay very good attention. So this is your cross-validation. DS, the confusing one is DS and cutoff, right? Look at that. The cutoff is not changing for some observations, right? And DS is the prediction for that. So DS is where we are. So if you're reading these numbers, so y hat lower, y hat upper, these are the numbers for this state. Okay. So for example, what is the prediction at month 5? 259. Okay. What is the cutoff? The cutoff is the first day that your prediction starts. So look at that. This is 312. This is 1 month before this. Okay. And then again, this is your first prediction, second prediction, your cutoff was there, third prediction, and etc. etc. Is this clear? When you see the daily data, it makes more sense, but again, so hopefully now you're not confused why this date is behind this date, because this is where we started making prediction. What was the prediction for the first one? Was this date. All right. Then off of this data set, if df_cd, I can call performance metrics. So this is also very interesting. So the performance metrics is something. I'm going to do another plot and then explain it here. First of all, it's going to summarize some time-series metrics for you: mean squared error, RNC, MAE, MAPE, etc., right? So let's do MAPE. So this is our mean absolute percentage error. And the way that it works in Facebook Prophet, which actually I found it interesting, is we have rolling. I'm not making a mistake yet. Rolling window 1. Okay. Remember, guys, we are this is the horizon for the entire thing. 730 is 2 years. 2 years is 24 months, right? This is the entire forecast horizon. Okay. If I say that the rolling window is equal to 1 means 100%. So use the entire horizon. And then, if you remember we did a bunch of cross-validation, go ahead and aggregate all of them. So this is the average of the mean squared, mean absolute percentage error for all those cutoffs for the entire time series, right? So this is, again, We have different cutoffs, and then we can calculate one. So let's explain to you. Imagine my forecasting horizon is this, and I'm not rolling over anything, right? So the rolling in is one, so use the entire thing. So I'm gonna say whatever, this is your forecasting horizon, whatever number you get here, the mate, just report it out. It's gonna be one number. Now, if I use cross-validation and roll this thing over, let's say I have multiple of these periods within my horizon, I can have a number, different mate numbers within that horizon. Take the average of that. So if I play it out with this ratio, hopefully you should follow. So if I say rolling window instead of 1, it's 10%, which by default is 10% profit. So what does this mean? It means that use a rolling window of 10% of the horizon size. What was your horizon size? The horizon size was 24 months. 10% is 2.4 months. 2.4 months is this dates. Does that make sense? And it's going to expand that thing, right? So it's going to roll it over. So it's going to say, okay, so within that 24 month, it obviously goes from this to 24 month, which is 700 days. 730 days, right? Within that horizon, go ahead and use these rolling windows and calculate mate for this different cutoffs. And you're expanding that cutoff. It's using the moving average. So giving the average of the first 2 months, first 4 months, first 6 months, first 8 months, all the way to first 24 months of your horizon. If your rolling window is 100%, it's going to give you one number for 24 months. If it is 10%, 10% increase it by that. Keep following? So that's why, if you're ever wondering why, is this a random number? No, this is not a random number. By default, it depends on what percentage of the data you use. If I do it 50%, then it's going to start from 12 months. Because my horizon was 2 years, 50% of 2 years is 1 year. So this is why we have 340 days. You following? Okay. So that's, I think, was a little tricky part that I didn't at all talk about it in the paper, but hopefully you understand it now. But the cool thing is that, let me actually make sure it's 10%. The cool thing is that once we do that, we can visualize these metrics over horizon days. Remember, I have 2 years, 703 days. And if I do 10% rolling window, it starts from 85, right? Or 89, something. But let's change our metric to month, right? I want to predict 24 months, 10% of it, 2.4 months. So this is 2.4, 2 months, actually, if you round it down. And now, as I'm expanding that horizon for forecasting, my mate, in this case, we're doing RMSE, or my RMSE is going to change. Okay? And if it is a stock price, what do you think is going to happen to your RMSE as you increase the forecast horizon? What's your guess? It's going to go up like crazy. Plug stock price data, and you will see that as you increase the forecasting horizon, if it is a daily data, they start to go crazy from the very first days of the forecast horizon. It goes up exponentially because it's hard to model that. And if you see if this line, like this is your metric for the forecasting horizon. If the forecasting horizon is increasing and this metric is kind of flat, the model is really awesome. You typically see an increase in this line, which makes sense because it's harder to predict way into the future. So the fact that this data set was super well behaved, so we are doing an okay job, right? And hopefully these observations make sense as well. So the great things, right? Because for each forecast horizon, I can have multiple, depending on cross-validation, I can have multiple mate. I take the average of that, and this is what I'm reporting. We can have the same thing for, that was RMSE, this is mate. Okay, that was pretty much it. Well, I'm not going to say it. Let me walk you through at a very high level about the next notebook. Again, this is one of those packages that you're gonna work with later on. So, but at a high level, so I call this one advanced version. we're not going to talk about tuning because we already did that at all. But let's see what is inside that one. So at a high level, a data set that I'm going to work with, this is a famous casual competition data set. It's called Rossmann Drugstore Sales Data. And it's a European drugstore. They have thousands of stores across Europe. And this is a task, right? We can look at data. Sorry. Well, this is a Kaggle competition. I think they gave $15,000 to the first winners. Your companies do that, if they want to improve their forecasts, they just put it on Kaggle and make a competition. I think it was 15,000 the first. But this is a data set, and then we have some information about each store. This is store information, and then let me actually read the task for you. So you're trying to predict daily sales for 1,115 different stores across Germany for up to 6 weeks in advance. So we're working with daily data, and then 6 weeks in advance. So it means 42 days, right? So we want to make forecast for 42 days. This is a key part. You're doing 1,000 different predictions, because each drugstore has its own data. You can make prediction. For example, for Walmart, you had 100, 200 different products, and you want to forecast the demand or sales of each product. Amazon, same story. So all these retail stores are dealing with the exact same setup. Okay. And so if you learn one of them, you're in good shape for any other task, right? So this is a task. Hopefully it makes sense. And the data provides historical data on sale, along with information about stores, promotions, holidays, and other factors potentially influencing sale. So you want to see that, okay, if this drugstore is offering some promotions, how does it impact your sales? Okay, so this is interesting, right? And guys, we're doing multivariate forecasting here. In this specific example, we can, because the variables that we're going to work is holidays or something about school holidays. And I can assume that going into the future, these variables are not going to change. So holidays, school holidays, public holiday, and things like that. There's one variable which is called promotion. We have to make an assumption. So I have some numbers that, for example, for this is store number 1, for this specific day, if you have promotion or not, right? When I'm ready to create that future data frame, I'm going to say, let's assume next 42 days is exactly the same as previous 42 days. Or next year is exactly the same as previous year in terms of promotion. It's a big assumption, and of course we have to there's no other way. There's no other way, because this is multivariate forecasting. And if you want to predict what happens 2 years from now, you have to predict so we'll have to promotion 2 years from now. You have to go with some naive benchmark. So typically use the last observation for what's going to happen in the future. This is what I'm going to do in this notebook, right? So in the notebook, we are going to do a couple of things, right? So the model that we put together, I'm going to put together 3 models. The first one is profit base model. So the base model is just nothing, right? I'm not adding any extra regressors. By the way, let me actually show you the data quickly. This is how the head of the data set looks like. I have 1,000 plus stores. Day of the week, I don't care, because as long as I have dates, day of the week is going to be taken care of. Sales, customers, open, promo, state holiday, school holiday, right? So these are interesting features that I can incorporate. And actually, the Rossmann drugstore, they want you to model this. What is the impact? Tell me what is the impact of promotion? What is the impact of school holiday or state holiday, right? So we're going to do that. And there's also this variable in the data, which is called customers. This is your target sales. What is a sale into the future? But we have customers too. We're not going to specifically use it for this task, but you can engineer some features. Because this is you working as a data scientist. Your job is this. Look at the data set. What can you do with that, right? So for example, if I have sales and customers, I can engineer another feature called sales per customer. Maybe that thing is more predictable or more intuitive, right? So this is the part that, it has something to do with your analytical skills as well, and it comes with practice, right? But the whole point is that I'm going to run 3 models. The first model, we call it profit-based model. Profit-based model just look at sales as a univariate time series. And I only do univariate time series, and I assume that everything is already reflected in sales. I don't care about anything else. And I'll run a simple time series forecasting with that variable and see how it performs. That's going to be my base model. Does that make sense? Then I'm going to say, you know what? First of all, so this is the base model. In the custom model, let's make some changes to this profit. I'm going to add holidays. I'm going to add seasonality. I'm going to play around with those parameters that I talked about. On top of that, I'm going to add some regressors. Okay. So let's go ahead and do that. So we have to prepare those regressors for next class, right? So the custom model is this. So this is what we're going to eventually do. I'm going to create my future data frame is now it has 3 columns. So again, this is going to get a little technical, but the point is that, do you remember for univariate time series, the future data set that you want to make prediction on only had DS? Now it has both school holidays and TOHOs. Okay. And I'm going to incorporate the public holidays indirectly. So I'm just using that holiday thing in Facebook Prophet, and then that's it, right? So when I create the model, I want you to look at the model. This is a fun part. Let me actually put together. Yeah, there you go. So I say, obviously I'm playing around with these change points and et cetera, et cetera. I'm adding holidays for Germany. I'm adding one regressor. I call it a school holiday in an additive way. And I'm adding another regressor promo in an additive. Do you see that this is kind of like neural network or something like that? Layers on top of each other. Does it make sense? Do you remember we talked about GAN, generalized additive models? This is the GAN component. These models are super complex, super flexible. Okay. And then we'll see how that performs. So this is going to be our custom model. I call it base model, custom model. And then, so this is the holiday effect. This is extra regressors effect, by the way. So, and then finally, I'm going to do some hyperparameter tuning. So obviously I'm going to do cross-validation, compare the performance of the 2 models. So this is the performance of the model 1, the base one. Look at the NAEP, 16% with a standard deviation of 5%. This is the model that we customize it. We add more regressors, which is the MAEP is 10%. So adding regressor for this data set was a big deal. Does it make sense? Okay. Adding promotions, adding holidays. And for business time series, typically it's a big deal. But the whole point is that, can I find enough of those regressors that I can predict them confidently for the future? So holiday is a typical example. And then we're going to do hyperparameter tuning. So hyperparameter tuning, this part is super simple. I'm going to create a dictionary. I call it parameter grid. This is exactly what we call in the machine learning course. I can play around with different things, right? So for example, 1, 2, 3, 4, 5. 5 different values for change points prior scale, 4 different values for seasonality prior scale. So 4 multiply 5. So I'm having 20 different combinations, right? So obviously you can play around with that. So, and then you are going to, again, create a model, run cross-validation in order to update the parameters. Go to the grid of parameters and find the best one. This is going to take a while, depending on your computer speed. And then we can plug the tuning results. So this is, you remember I have 20 different combinations. And for each combination, it's going to give me a 1 NAEP. And then I'll pick the smallest one. So here it seems that the combination number 3, which was
prior scale 0.001 and seasonality 10 was the best one. Basically says that we don't need to have much change points, and then let the seasonalities take control of everything. So this is how I read these numbers. Okay. And yeah, you can see what are the best parameters. And once you're done with that, you can go back and retune your custom model with optimized hyperparameter. This part is pretty much the same as what we did in machine learning, right? We play around with these things in machine learning a lot. We tune hyperparameters. We went over grid search, and then we find the best one, wins back. But just remember, when you say best parameter, this is best as far as you are. This is as good as your grid search. Your grid search was only looking into 20 combinations. So maybe, can you do better? Of course. Can you afford to do better? It depends on your complete route. All right, so that was pretty much it.
So until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.